In Part C, we'll be studying the inverse CDF of the uniform distribution. Quantile is also another term for this. We'll be given probabilities and try to find ranges of value that match that probability. First, though, let's go back to just finding the probability. So if the time I wait at a doctor's office is uniformly distributed between 4 minutes to 25 minutes, then we're letting x be my random variable, which is a measurement of my wait time. Then what's the probability I wait more than 20 minutes? Pause here, you try, then check back. It looks like I would wait this amount of time around 24% of the time. So I take the area between 20 and 25, that's underneath the PDF, and I know the height of this PDF should be 1 over 21, because the total area needs to equal 1, and it has a length of 21. What wait time is unusually long? Here, this is an example dealing with quantiles. If we were to picture this, we have a wait time anywhere between 4 to 25 minutes, and we know that unusual values should occur within about 5% of the time or less. So we want an unusually large value so that the area, which corresponds to probability, should be 5%. So we need to figure out what value v would correspond to this. So we're trying to find a v, a particular x value, such that the probability that x is larger than this v equals 5%. The uniform distribution is nice to work with because we're dealing with rectangles. So we need to figure out what rectangle will have an area of 0.05. We know that rectangles would have a length times width, or in this case height. And this, how long is this rectangle? It starts at v and goes to 25, so we take 25 minus v to find its length, multiplied by the height, which we know is 1 over 21. So now we're going to try to solve this for v. I'll multiply both sides by 21 times 21 equals 25 minus v. And here I'll add v to both sides and then subtract this thing from both sides. And I'll get v equals 25 minus 0.05 times 21. Now let's check with my calculator. And I get v equals 23.95 minutes. So if I were to wait for, say, 24 minutes, that would be unusually long wait time for me. What wait time is unusually short? Why don't you pause here and try to figure out on your own, then check back with my answer. Here, I tried to find an x value I labeled u, such that the probability that x is less than u was 5%. Figuring it out geometrically from the rectangle, I have a length of u minus 4 times a height of 1 over 21 equaling 0.5, so u equals 5.05. So if I were to wait 5 minutes or less, that would be unusually short wait time. So what's the minimum wait time I have 10% of the time? You try this, pause here, then check back. Here, I'm trying to find the 10th percentile of my wait time. So I'm trying to figure out what particular value v would have a probability of it being less than this, equaling 0.1. So v equals 21 times 0.1 plus 4, which is 6.1 minutes. So 10% of the time, I wait 6.1 minutes or less. The rest of the time, I would wait more. So between 6.1 minutes all the way up to 25 minutes. At most, what time do I wait? 90% of the time. If I were to just ask, what time do I wait at the very most? Well, we know that at the very most I wait 25 minutes. But 90% of the time, what's the most that I have to wait? We are now trying to find a specific value, we'll call this V, that will be the most I wait 90% of the time. X is less than V, which should equal 0.9. Now we can find this by using, okay, the area of this rectangle is going to equal 0.9. Which will be height, and we know that that's going to be 1 over 21, times the width, which would be V minus 4. Now we just need to solve this for V. After a little algebra, we receive V equals 22.9 minutes. Now I want you to try 26. Find x sub 0.01. So this is the notation that we found on page 100. Check that out, then find the value. Here, the notation x sub alpha is used to denote how much of the x values would be to the right of it. So if we want 1% of all the x values to be to the right of this particular x value, then the proportion or area to the right needs to be 0.01. So we can use geometry. We have this area, which equals height times length, which would be here the length is starting at 25, go back, so take away this much from it. Solve this for x, so x sub 0.01 equals this, 24.79 minutes. So x sub 0.01 equals 24.79 minutes, which means that only about 1% of the time would I have to wait more than this, and 99% of the time I need to wait less than this value. After finding all of these particular values that correspond to probabilities, for instance, having a 5% to the right or 5% to the left, let's find the general quantile function. So recall that the uniform CDF is given by f of x equals this. We'll let this equal p, the certain probability. Now if we solve this equation for x, the value that corresponds to a particular probability p, then we'll have the function that will define our uniform quantile function. So let x be uniformly distributed from a to b. P is a probability that's between 0 and 1. Then we can have f of x sub 1 minus p equals p. That is to say, if we have a certain x value, given a certain proportion of our data, p, is to the left of x, then 1 minus p will be to the right of x. Now, this function, the CDF, gives us we can now find the general quantile function. So recall that the CDF for the uniform distribution is this. Now if we were to just isolate the important part when p is between 0 and 1 but not those actual numbers, then we can solve this for x. So we'll let p equal the CDF. Solve now the part where p is between 0 and 1 for x. And what we'll receive is this equation right here, x equals this. But just to keep track of what's what, we'll label x x sub 1 minus p. So recall that this subscript tells us that a certain probability is to the right. And if we know that p proportion is to the left of x, then 1 minus p would be to the right. Thus, the CDF function of x 1 minus p equals p. And so if we take the inverse of this, the inverse CDF of p would be x sub 1 minus p, which it turns out, once we solve for this, is the proportion times the range b minus a plus a. We can now find the general quantile function for this uniform distribution. So recall that the CDF, which brings x values and has an output of probabilities, is f of x equals x minus a all over b minus a, as long as x is between the a and b. And it's 0 when x is less than a, and 1 when x is greater than b. Well, it looks like the important part is right here. So to find the inverse, we need to label this with a new variable, call this p. So p equals f of x. Now we'll solve this important part, p equals x minus a over b minus a for x. And what we'll receive is x equals this, p times the range b minus a plus a. But just to keep track of which x this is in particular, we'll give it this new notation, x sub 1 minus p. The 1 minus p proportion is to the right of this x value, and p would be to the left of it. What happens if p actually equals 0? Well, then we know that that would correspond to the x value a, and if p equals 1, we know that would correspond to x value of b. Although this is quite helpful, it's not something that you need to memorize. As we've shown before, we can quite easily just use geometry and area of rectangles to help us find a particular x value that would correspond to so much of the proportion of x values being less than it, or a certain proportion being greater than it,